switching on.
Как пойдет?
Yes. Please
You're good?
get to thermodynamic equilibrium before we start. Okay, so it's a pleasure to present next speaker, Igor. Oh, MAZIN, sorry. I got it.
Well,
Igor MAZIN was, as I see, I was intrigued by the name of George Zawadzki on the slide.
George know him very well.
Yes, yeah, he's a legend in the Netherlands, so that's why I was.
He's a great mind. No, I put him in here because it actually the whole idea of two-dimensionality in altermagnetism came out from one of our casual conversations with George at some point of time. On Zoom, of course, because now George doesn't show up in person. So I had to, I'm not saying it as an excuse, but rather an encouragement. For some reason, I believed that my talk was 25 minutes. So I prepared material to a very tight, well-packed 25 minutes talk. So hopefully you'll have enough time for questions, discussions, and just banter. All right, so this work, we were working on that together with Libor. As I say, George initiated that. And let me see. So I will sort of touch upon three issues: to D or not to D, and is altermagnetism in monolayer. I think it's actually a less trivial question than you may think. I remember that when I first showed Libor my first candidate, his first reaction said that that cannot work, and I will explain you why. Later we realized it does work, and it works in a less than trivial way. Then, in fact, I don't know any existing reported two-dimensional single-layer antiferromagnet which would have been readily altermagnetic. The question is whether you can pound it with something or just, or using fancy words, functionalize it in a way that it would show altermagnetic properties.
I was saying is you were saying functionalization.
Yes, yeah. In fact, I didn't know any American or any English analog, and I couldn't find any, so probably it doesn't exist. But in Russian, it's a very well-known saying. If you then they're going back to this issue of whether it can or cannot be. It turns out that it can have very interesting, in some sense, more symmetry than you would think just looking at the crystal structure. And of course, when you say the word symmetry, it's a strong temptation to quote from Blake immediately, as most of you probably know. So first of all, to begin with, what is not to the altermagnet? Because there was one report in the literature when was something which was showing transport or shows properties which could be mistaken with altermagnetic, and in fact the paper by these two gentlemen was called Colossal Splitting in the Monolayer of Collinear Antiferromagnet MnF2, and it's not an antiferromagnet. It's a different beast, which we call Lattice Compensated Ferrimagnet. And I will explain you in a second what is the difference between symmetry compensation, the notion that was brought up quite several times yesterday, basically as a definition of altermagnet, and this different type of property which we call lattice compensation. So this is the particular slice, monolayer of existing material MnF2, and it turns out that this is my picture. In the paper, there was no labeling because these are all manganese. But if you actually do crystallography, you can see that half of these manganese have Wyckoff position of 1e. It's a pleasure to be in an audience where you don't need to explain what Wyckoff positions are. That's very good. And the others are 1h. So in some sense, crystallographically, they're just two different animals. So in this sense, it's not antiferromagnet at all. And the density of states for spin up and spin down channels are completely different. However, this manganese here is 2+, and again, as most of you, probably all of you know very well, manganese 2+ is a very stable magnetic ion, which really likes to be in the 5-half spin state and nothing else. Now, this is an insulator. If it is an insulator, then by definition, its magnetic moment in the spin-up channel and the spin-down channel must be both integer. So the net, by Lattinger theorem, so the net magnetic moment can be -1, 0, 1, 2 Bohr magneton, but or exactly 0. So it cannot be close to 0. If it's small, it must be exactly 0. And that's what we call lattice compensation. If you do band structure calculations for that, you can see the bands are split and everything. It's just ferromagnetic structure. Now, so that's very interesting, but it's not what we want. Now, what do we want? What is a collinear monolayer antiferromagnet? Well, there are not that many, but there are quite a few. And one of the most common example is manganese PS3, MnPS3, which can also be selenium, which will become important in a few slides. So it's MnPS3 monolayer. You can see the structure here. And it has a layer of sulfur above and a layer of sulfur below. And it has inversion symmetry. And not just inversion symmetry, it actually has inversion symmetry right in the middle of this antiferromagnetic manganese-manganese bond. So this inversion symmetry is an operation which ensures spin compensation. So this is conventional antiferromagnet. This is the crystallographic information to this effect. Now, if you do obviously, if you do calculations, you find that Fermi surface, this is also an insulator, so you have to cut at some finite energy. So not really Fermi, isoenergetic surface, just some random one. It's completely spin degenerate. You look at the bands are completely spin degenerate, nothing interesting. So there are 3 different ways of convert this beast into altermagnet. One is Janusization. Those who work with dichalcogenides are familiar with this notion of Janus compounds. It's very common in materials which we call TMD, transition metal dichalcogenides. So I don't know how they do that, but experimentalists can actually manufacture structures which have sulfur on one side and selenium on the other side. So in this case, as you can see, this point that used to be inversion symmetry is not anymore. So this inversion symmetry operation does not map one lattice upon the other. But there is still a symmetry operation, it's actually quite a few. For instance, there is Roth inversion that maps one sublattice onto the other. So it is still by symmetry compensated. But this symmetry operation now is not translation, is not inversion. Yes, Revaz.
Since you mentioned inversion several times.
Yeah.
And in general, in the solid state setting, you have a substrate and you probably have an overlay.
Very good question. Wait for the answer. It will be, yeah, the second course is coming. Okay. All right. So, but even for a freestanding material, this way we can break this inversion symmetry while still retaining some other symmetries which enforce zero net magnetization. So now that becomes altermagnetic. And you can actually do calculations. And this is, it's actually, I will show you on the next slide, the path. It's, you need to select specific low symmetry direction, and then you can get this spin splitting. In fact, this is green and blue are 2 spins. Just because Libor asked for that, I also superimpose that with spin orbit coupling calculations, and you can see that this crossing is lifted and so on, and that will eventually manifest itself into some anomalous magnetic transport properties, like here. So we have, again, you can use the table in this famous Libor, Thomas, and Jairo paper, which lists all magnetic point groups that altermagnets can have. And you can see that if your magnetization is perpendicular to the plane, then this is this magnetic point group is this one, and there's no there's no anomalous Hall effect because it's an insulator, but you can calculate the Kerr rotation angle, for instance. If you have magnetic moment in the plane, it can be 1, 0, 0, or in this is not unless what I basically mean this is x and this is y. Not a very fortunate notation. So you can have either one or all three components of the conductivity non-zero. So this is what is plotted here is actually not exactly Kerr angle. It's just non-diagonal components of the. Oh no, sorry, no. This is Kerr angle in degrees. Yeah. Right. So just to reiterate that spin orbit coupling is, of course, depends on orientation. It's maybe trivial for most of you. It's not particularly small for 0, 0, 1, but it's sort of compensated by symmetry, and there is no non-diagonal optical matrix elements here. So now the second way of functionalizing this thing is gating. So these calculations I will show you, they are performed for a relatively large electric field gating, relatively large but not unheard of. Let's put it in this way, shall we say. So again, you do calculations and you can see the same story. So this low symmetry direction is spin split and high symmetry directions are not. The symmetry is broken in exactly the same way. The main thing is that you essentially break this glide plane and that reflects in breaking inversion. Now you calculate the Fermi surface for this case, for instance, and you see that the Fermi surface, not isosurface, somewhere here I'm cutting now, and it's spin split. In spin split in an interesting way, which we will discuss in a moment. And now to reverse question, one other way is to include in your calculations a substrate. So in order to do that, we need to find
and an overlayer. An overlayer, which may be different.
or maybe overlayer, or so, yeah. So this is, yeah. Yeah, exactly. This is a simple example, and I choose this example. I don't know if it has been ever, apparently never done experimentally, but just from the tables, you can see that molybdenum telluride has nearly perfect matching with this compound, like a fraction of % matching. So theoretically, you should be able to grow that. If you do that, then you obviously, as Rivas pointed out, you break conversion symmetry as well. And now you have there's a lot of bands which are coming from molybdenum ditelluride, which are not split because they're not magnetic. Somewhere here below, there is the lower Hubbard band of manganese starts, and this is pretty decently split. So you can also cut, for instance, here, and you can see that you have very interesting Fermi surface, which some of the Fermi sources very strongly spin split, while others are not really. And you can also look at that more carefully. And before doing that, that will be there's later this talk. I think. Oh yeah, I see the speaker here. There will be talk about octupole magnetic moment, and that's what happened. Yeah, and there will be. I will ask the speaker the question, which I just want. That I don't want. We will not be able to show this picture again. So this is manganese telluride in altermagnetic structure. So this by symmetry, so obviously the magnetization density around this red and blue ion has octupolar component. It's not related to my talk at all, but the question that if you can also imagine magnetic substance, actually such materials also exist, where magnetic ions are these light brown ions. There are 2 formal units per cell. And then they would be, this would be up and this would be down. And that turns out to be not altermagnetic because there is an inversion center. But now each of them is sitting in prismatic environment, and I would have thought that this should also have octupolar moments. So this is just the questions that I'm going to ask 2 talks forward. But now going back to our work, so let me compare this. So we have this, many people did calculations for this guy as well. And if you look from the top at the Fermi surface, you can see that the Fermi surface has this shape. So this blue is one, or again, isosurface is one spin channel, red is another spin channel, and you can see that this has 3-fold symmetry, right? So each spin, the spin has 3-fold symmetry. But you can immediately say, but well, we've heard multiple times here, then the spin polarization is invariant under inversion. Spatial inversion. And yes, that is indeed true. And before showing that, let me ask people, that is another Fermi surface from a completely different compound, and it's not magnetic, but it has spin orbit coupling and no inversion symmetry. Anybody knows what Fermi surface is this?
It's some transition metal they call coordinate spin orbit, for instance?
Yes. Yes, I was looking for Belzig. I don't see him here in the room. Ah, here you are. So you should have recognized that. Yeah, yeah. This is actually, this is niobium diselenide, this famous Ising superconductor. Yeah, and you can see that it has exactly the same spin splitting as this guy. And this is truly 2-dimensional monolayer material. So where is the catch? And the catch is here. Why this thing doesn't, oh God. That's a problem. That is the problem. Give me just a second. Let me, because this is, I just need to remove. And start again. Because that's important. Now, yeah. Now it works. So this is how the thing looks in 3 dimensions. It's a three-dimensional material. So you can see that this is a sort of this Ising spin orbit splitting that we had in niobium diselenide repeats itself for negative Kz with the opposite sign. So as a result, the true spatial inversion still doesn't change spin splitting. So now, and as the problem comes up, but now we have a true single layer, and that's what Libor pointed out when I showed him that, well, this thing should have nodal plane at Kz0, so you shouldn't have any spin splitting, but we do. And what happens is the following. So this is in Libor's notation, this has G, right? Yeah, this is G splitting, so it has 3-fold symmetry. But nothing prevents us from even though this is the lowest symmetry required by crystallography, nothing forbids us from generating an I symmetry altermagnet with not with this 3-nodal plane, but with 6-nodal plane. And
G is 4.
so no, that's G. Then A, B, C, D, G.
I will be 6.
I is 6, and that would be. Okay, hold on, don't confuse me. What is what is this?
This is G.
That is G.
This is
4 nodal planes.
yeah, this is G, and this is I. No, so the next one will be I. Yeah, yeah, this is I. Yeah.
Yes.
So this is G, this is I. We jump 2 letters, right? Okay, good. So what? But basically, what happens is that instead of 3 nodal planes, we now have 6 nodal planes. So this thing sort of like elevated itself to a higher symmetry and remained altermagnetic, which is very neat. Again, so we can, okay, so now we are finished with that. And let me just add that we can calculate, and actually we have calculations for this core angular rotation for all 3 guys. They're all in measurable range. Let's put it this way. So, and now with that, I'm going to the second part of the talk, and that's much more controversial. It's an iron-selenium monolayer on strontium titanate. Those who have even marginal interest in superconductivity should have heard about this thing. It's supposed to have the highest critical temperature among all iron-based superconductors. There's a very interesting controversy there. There was just recently a paper which was claiming that even though the gap opens at something like 90 Kelvin, the actual diamagnetic superconductivity occurs much lower. So anyway, this is a very controversial, very interesting, definitely, material, and nobody fully understands this. And in the band structure calculations, people did it many times, the ground state is so-called stripe order, which is the order corresponding to doubling of the unit cell and definitely not altermagnetic. However, it was brought quite a few times before a hypothetical possibility that maybe as opposed to bulk materials which are known to have stripe order, these have checkerboard order. The reason why people brought it up is that if you, one of the biggest problem for this class of material, specifically for this material, is that it shows a Fermi surface pocket at gamma, which experiment doesn't see. And people try various ways to beat this hair with LDA plus U, DMFT, whatnot, never could get it. It turns out, and I think it's probably largely accidental, that if you do checkerboard and apply, do LDA plus U, this pocket disappears. Again, it's a itinerant magnet, so LDA plus U are questionable. There are many questionable part there. But the fact is that if you assume that you get band structure which is more close to experiment than the one that you get without magnetism or with checkerboard magnetism. Now, why is it interesting for us? Because for checkerboard order, for individual single layer checkerboard order iron-selenium plane, there is inversion center between two irons, and this inversion center provides antiferromagnetic symmetry operation. Now, if you remove this inversion symmetry in any of the discussed previously ways, particularly if it is epitaxial deposited on STO, which people do routinely, then this symmetry is broken and it becomes altermagnetic. Now, yeah, that's what I was talking about. Why we got interested in that? Because there were two recent papers. They were discussing iron-selenium monolayer, or I will switch to that later, iron-selenium surface states. So this was a paper which was posted on Conmat last year in October, not published yet. What they were measuring electron energy loss. And that's the title. Forget about this non-trivial topological state. That's probably not relevant to anything. But what they found is that they can get energy loss for spin polarized electrons with left polarization, right polarization. They have different energy loss curves. Now, in order to understand that, and they also see two phonons plus electron background. Amazingly, the ratio of the asymmetry remains exactly the same, whether you have a phonon or whether you have electronic background. Now, in order to understand that, you need to think about the diagram which describes this energy loss, a so-called optical diagram. Basically, you have an incoming particle which you square to get energy loss, and this is the excitation that is being excited inside the material. It can be a plasmon, in which case it is imaginary part of 1 over electronic epsilon, or it can be a phonon. And it's the same, exactly the same thing as Raman scattering. So as Raman intensity, as we all know, in the polarization channel of IS, incoming scattered, is given by the derivative of the dielectric function with respect to the normal coordinate of this excitation. So what does it, why am I telling that all? What I'm telling it to tell you that in these two cases, the inert of these diagrams are completely different. And the only way how this asymmetry will be completely independent on what excitation you are exciting if this asymmetry is sitting in the vortex. And that can happen if your dielectric function to begin with has non-diagonal components, which would be left and right oriented. So they, in the paper, they come up with some completely different explanation, which were basically ascribed to the excitation itself, which I think doesn't hold water in view of this complete independence on the character of excitation. So, but if that's in matrix elements, that it means that the electronic structure itself must support non-diagonal dielectric functions, so magneto-optics. And in order to do that, we calculated this asymmetry, which is essentially the, in principle, it should be this derivative of epsilon, but that I cannot calculate, but I can calculate just the ratio of the dielectric function, real and imaginary part of the dielectric function in diagonal channel and non-diagonal channel. And you can see that they are different by 2 to 3 order of magnitude. So this is the asymmetry of 0.01, about 1%. So that's good that this asymmetry exists. What is not that good is that experimentally it's 10 times larger. But I would say that given the complete wave, hand-waving character of this assignment, maybe just 1 order of magnitude difference is not too bad. The main fact is that qualitatively the effect is there. And there is another separate check of this interpretation. You know that this altermagnetic effect can only occur if you are probing iron bands. Iron bands are, the width of iron bands is about 5-6 electron volts. So after that, you're not probing iron bands anymore. So this effect should go down rapidly. And indeed, when they measure that as a function of incident electron energy, it's about, remains more or less constant up to about this 4 or 5, and then it starts rapidly decaying, and if it's larger than 7, it becomes 10 times smaller, exactly where the iron band ends. All right, the second part of the same story is iron-selenium surface. So this is this simulation that in this actual calculations, in fact, this slab has inversion symmetry, but this inversion symmetry is not anti-ferromagnetic operation. It basically maps spin upon itself, not one spin upon the other. And because of that, you can clearly see at some points, you can see altermagnetic band splitting, which would, why are we interested in that? The reason is that there was this paper, also published just recently, and they were claiming explicitly that they see time reversal. They basically measure Kerr. They measure Kerr effect on the surface, and they can see that it's non-zero. Very small, you know, this is 10 to the minus 9 radians, and it goes up to 100, so it's 10 to minus 7 radians, but clearly measurable. And they say that there must be surface ferromagnetic order. Now, in order to understand it, forcing it, you can, as a DFT person, the first thing you do is try to calculate the energy of different states that may be involved there. The ground state, as I say, in DFT, ground state is stripe order, which doesn't work. Nail order, so checkerboard order, is about 50 millivolts higher. But ferromagnetic order is like 500 millivolts higher. So basically, from DFT point of view, that the system might be massaged, having in mind that there's some effects beyond DFT which are not counted, that makes the surface order in checkerboard fashion. There is literally nothing in the world that can make it order ferromagnetically. It's just impossible. So with this in mind, I made this assumption that it's checkerboard and calculated the Kerr rotation. This is my Kerr angle. Now you can see that I have an opposite problem. So this is in degrees. So I'm basically 4 orders of magnitude too large. But that's actually not that big of a problem. Because first of all, as we again was discussed multiple times previously, there are always antiferromagnetic domains, altermagnetic domains, which largely compensate each other. So what they measure is basically imbalance of these domains. The other thing, of course, is the penetration depth of light is a pretty large. Light penetrates several dozens of layers. And that dilutes this effect if it's just single surface layer. So bring it down from what happened? Bring it down from this calculated number to something comparable to experiment. It's not a big problem. There are many things that can make this experiment smaller. So that's I think it's a very plausible explanation. Definitely more plausible than what the authors suggest. So. These are these two systems that I have so far, and I have nothing more to tell you guys, so just ask questions or we can discuss anything else.